So my name is René. I'm a professor of biomedical engineering at Johns Hopkins. I'm the director of the Mathematical Institute for Data Science. In terms of research, I do computer vision, a variety of problems in computer vision, from semantic segmentation to video segmentation and dynamic textures. I also work in medical imaging, or more broadly, biomedical data science at various levels, from developing a new blood tests to classification of stem cells to brain imaging to figuring out how skillful a surgeon is at doing surgery, and that's what I will speak next Friday, in fact. But I also work in machine learning. Much of my career has been on unsupervised learning and clustering and dimension reduction and manifolds. But what I will be speaking about today is about the mathematics of deep learning. The first lecture before lunch would be about the question of optimization. How can you guarantee that you find a global optimum when you train a deep network? And the second talk right after lunch would be about dropout, which is a mechanism for training neural networks and trying to understand what it actually does and why it works or why it doesn't from a theoretical perspective. So I'll begin a little bit with the history of not computer vision, but of deep networks, and with perhaps a little bit of a twist on the mathematics of it. So neural networks began even before computer vision. They began in the 1940s, and the first networks were primarily just neurons, and they were primarily binary, so trying to predict zeros or ones, really. And what is interesting is that even the first training algorithm was developed around the 1960s. It's the precursor of backpropagation, and it was called Adaline because I think it has to do something with adaptive linear or something like that, but just for these perceptions. So what was very interesting is that there's been not one neural winter, but there's been two. And obviously, there are many reasons that are practical as to why people abandoned deep networks twice. But some of the reasons are interestingly theoretical. So there was this paper by Minsky, which is the same person that kind of opened up the computer vision field, where he showed that these simple neural networks with just one perception and binary, they couldn't predict one of the simplest functions, which is called XOR. And, you know, they thought at the time that if it cannot predict one super simple function, it's not going to predict much more complex ones. So there was already a first winter in the 70s where people sort of abandoned the idea of using deep networks. Then, as already been said, the PhD thesis of Werbos, together with the invention of the backpropagation, were sort of the revival of it. And indeed, it was around the 1980s. Although if you think about what backpropagation is gradient descent, right? And then the chain rule. So we might as well say that it was Leibniz who invented it in the 1600s. The key ingredient, I think, that made it very popular in the 90s and 80s was the applications to digits that was already mentioned, the convolutional neural networks, but also in speech. I think the LSTMs sort of started to appear in the late 90s. But again, there was actually, I would argue, a second winter that happens in most of the 2000s. And I would argue that a piece of it was that, as was argued in the morning, it didn't work for other things other than digits and faces, and so that's true. But there were other reasons, I think, and the reasons were that these networks were seen as black boxes. At the time was more or less the times that the linear classifiers and SVMs appeared, and if you think about training a linear classifier, it's a quadratic optimization problem. So it's convex. We could have guarantees that we found the minimum, And because there was only one minimum, we could try to understand how well it generalizes to unseen examples, which are kind of the critical problems in machine learning. But for deep networks, it was non-convex. There could be many minima, and generalization was completely non-understood. So by and large, they were seen as black boxes. And so that meant that people said, well, I will probably be much better by designing my own features and feed them to a classifier. And those classifiers would be SVMs or boosting, as was mentioned earlier. So what happened around year 2012, I think you all know, so let me just flash very briefly. The performance of object recognition methods went down from 26 to about 15% in 2012, so 10% improvement. Blue is non-deep learning methods. Red is deep learning methods. And everything quickly became red, down to 11%, down to 6%, down to 3%, and probably today is like 2% or less. The same thing happened in speech recognition. So this is the x-axis is the year, and you are probably too young, but 10 years ago you would call an airline and you would get very upset at your phone as to how bad talking to an airline was. Siri was a little bit better for a while, but Alexa really nailed it, and a lot of it actually is deep learning technology that came from Hopkins, from the speech group. But we're not very smart at Hopkins at getting money for it, so Alexa got all the credit. The same thing is true about games. This AlphaGo defeated the world champion of Go. It's been extended to other games. But I think we're all here because we all believe that the next wave of deep learning techniques will be really revolutionizing medical imaging and more broadly biomedical data science. And we're already starting to see huge predictions about the number of startups in the biotech spectrum about using deep learning technology for really a wide variety of applications. And the big companies are already investing, both Google as well as IBM, for doing deep learning in the medical domain. Fine, great. But what if you're more interested in the math of it and you say, okay, it's working so well, so there must be some reason as to why it's working so well. So if you've never actually tried them yourself, you might ask the people who tried them, and they might tell you, well, one major difference is that instead of having to handcraft these SIFTs and HOG or whatever your favorite feature is, now these features are automatically learned, and therefore they have to be better because they're trained for the particular task you have in mind. A theoretician would actually argue that, well, yes, we've replaced handcrafted features by learned features. But what we have actually done is to replace them by handcrafted architectures. Because every paper is just trial and error as to what architecture to use. The same thing we were doing with the features 10 years ago. What are the reasons? The other reason is that you have to use more layers because they capture more invariances. We want to be invariants to viewpoint, to lighting, to a variety of other things. And these experiments from 2014, X is the number of layers, Y is the mean average precision in some computer vision data sets. And sure, in practice, that's better. But we just had the example in the previous talk about, do I use wide filters and a few layers, or do I do very tiny filters and a lot of layers? And it seems to be that deep is better. But is there a reason as to why that is the case? When you look at the networks from the 80s versus the networks today, in fact, if you look at them, there is not a lot of changes. It's pretty much the same thing, except that there is a lot more data, and because the data is bigger, and you have GPUs, by the way, were used even earlier. They're not really part of the deep learning revolution, but with more computing, and what else changed? Here's the first thing that changed, perhaps, is this regularization technique. So in the old times, we were told to go by the book of machine learning, that the bigger your model, the better you will feed your data. But maybe you will not be so good at predicting new examples. And so you could overfit, and so you needed to regularize. And the way to regularize is sum of the square of the weights was kind of the classical way. But here instead, this is new relative to the 80s. The idea is randomly pick half of your weights, zero out the outputs in the forward pass, and don't update the weights in the backward pass. Why does that make sense? Well, you ask people around, is that formal regularization, or can you have a theorem about what it does? And by and large, they say that it tries to make all of the weights equal. And then you ask them, can you write that down? I mean, are the weights identical? Well, no, more or less. And well, what is more or less? And so when you try to make these things precise, it becomes a little bit difficult. So they also say that dropout is doing some form of implicit regularization as opposed to the explicit one that would have been to penalize the extra weights. But what does that mean? What is the actual effect? Can you actually show that the machine will generalize better? I don't think it's been done yet. The other change, and the previous talk mentioned a variety of nonlinearities, but it was very popular in the 80s to use these sigmoids. I guess maybe the inspiration was from biology, that you wanted this kind of model, the neuron is off or on, kind of. But now it's this rectified linear units that is zero or linear. And when you ask the people that work on this why, this is the classical answer I hear. They say it's because of the vanishing gradient problem. I say, what is that? Well, if you look at this sigmoid, the gradient is kind of zero, and the gradient is kind of zero. And so here is the good part. And the problem is that if your gradient is small, your algorithm will get stuck, and that's why it doesn't work. While if you use the ReLU, then they say, here the gradient is just the identity, so then you're not going to get stuck. And so now we're all happy, and we think that that's a good answer. But you give that answer to a mathematician or to someone who works in optimization, they say, and so what? That does not mean that you're going to find an optimum just because your gradient kind of vanishes or kind of not vanishes. That may be just a numerical issue, but it has nothing really to do with whether you can find that global optimum. So I think it's fair to say that the theoretical understanding of deep networks remains very shallow. So when thinking about, well, what kind of questions should I ask? What do I really need to understand? Do I really need to understand them? So I think these are the three areas that I think are at the core of understanding what deep learning, or the reasons why this deep learning might succeed. I think the first one, and I hinted towards that when I said these mostly handcrafted architectures today, is really the question of how do you design them? Okay, how should I design the architecture? The second one is, this is what an SVM would look like, but this is maybe what a deep network would look like. Namely, there might be many global minimizers that have the same value. Or maybe the thing is even more complicated. I have local maxima, local minima, completely flat regions where the error surface is about the same, and so on and so forth. And the last, and maybe that's the most important from a machine learning perspective, is I train the network on data, but I want to test it in a different data set. So I want to understand how well it generalizes. And this cartoon picture sort of shows here two classes, and that shows the boundary between the two. And so the idea here is that if you perturb the red one a little bit, probably the class is not going to change. So somewhat there is this intuition that simple boundaries would lead to good generalization. Well, if you have something like this, where the boundary is kind of very complicated, right? A small perturbation of the red would move you to the blue class. So that probably doesn't generalize well. So if we had a way of understanding what the boundaries are, we could probably try to predict how well they do, more from a theoretical perspective. Now, these three questions are by no means new in any way. So the question of the architecture is how many layers, what is the size, what nonlinearities, how should I put them together, and so on and so forth. And back in the 90s and 80s, this question was already studied. And in fact, it was studied for the simplest possible network, just one hidden layer. And they had this very nice theorem that says that neural networks with one hidden layer are the so-called universal approximators. What does that mean? That you give me any function, f of x, probably some requirements. I think continuous is one of the requirements. And you can approximate it within any epsilon. So that immediately begs for the question of why do we need deep networks? Like one hidden layer already can approximate anything within epsilon. And so if you want to see actually what is the theorem, more precisely, here it is. Pick any function that it needs to be continuous. Pick any epsilon. Then there exists, n is the number of neurons, okay? And there exists a set of weights such that this function, which is the function of the neural network, right? Dot product with the first set of weights, the nonlinearity is right there, and the output weights are here. And the error between the two is less than epsilon, okay? So, so this has motivated research in the last 3, 4, 5 years trying to understand why deep is better than shallow. And what is the reason why deep is better than shallow? It was actually already known in '92, more or less, which was, for example, this is if I train a network to predict some function, what is the error that I make, the prediction error, during training? And here you can see, for example, the dependency k is maybe the number of training points, okay? So in order to get, the issue is the following. Sure, the network can predict any function within epsilon. But to achieve that epsilon, I might need a very, 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 very large number of neurons. So a very wide network. And so the guess, and what recent papers are trying to show, and I think let me just point out to one paper, gaps between deep and shallow networks, is that with the same number of neurons, I can probably reduce the error more if I use deeper networks than if I use shallow networks. So again, it's a question of not just I need to achieve an approximation within epsilon, but how many neurons do I need to do that? Okay, generalization. So again, I train a network on some training set, and I want to make sure it works well on my test set. That's what generalization is about. And suppose that the classical example is, suppose that I just had data on a line, and I hypothesize, do I just fit a line? Do I fit a quadratic? Do I fit a cubic? And so on and so forth. So clearly, as you add a higher order polynomial, you can pass through every single data point and achieve absolutely zero error, right? Eventually, if you have a degree that is large enough, zero error. But if you now sample a new point, most polynomials will, go to infinity or not. So they might do very bad predictions outside the set. So a line might be a much better model. So that's exactly what this question of regularization is, that you have to penalize somehow the complexity of the model. So in the case of polynomials, you might say, I want polynomials of lower degree. In the case of neural networks, you might say, I want networks of smaller size. So there is a little bit of contradiction here between big networks probably express more things and would allow me to do more complex problems. But big networks might not generalize as well. So this is kind of trying to say, choose your network a little bit smaller. But the challenge is that how do I measure the complexity of a network? And the most natural thing is number of parameters. So if you look at the literature from the 80s, they would say typically that the number of training examples that are needed is kind of quadratic on the number of parameters. So if you had a network with 10 parameters, I'll need 100 examples. If I had a network with 100 parameters, I need 10 to the 4. If I had a network with 60 million parameters, which one is that? The AlexNet. How many images would you need to train it? 60 million squared. All right. How many images are there in ImageNet? I think it's just about 1 million, right? And so we live today in a situation that is completely against the history and the theory, namely that the amount of training data we have is significantly smaller than the size of the networks we're training. And why does it still work? Probably the answer is because the theory from the 80s was maybe over pessimistic. Or maybe another answer is that maybe we're not counting right. Namely, the complexity of a network is not really the number of parameters, but maybe something else. And the open theoretical problem is to figure out precisely how do you measure that capacity of the network so that you can put that when you are doing the regularization. So as I said, this I already mentioned. These are the results from the 80s. The number of training examples grows with the network size. But today, and I mentioned this already, we control the size via this procedure of dropout. And so I just asked the question, what does dropout have to do with the number of weights or with the capacity of the network? Why is it really controlling the size? Why is it working so well? So we don't know. So there's been recently a lot of studies on how to do this. And let me just mention maybe two that are interesting. Let me point out to this one, this product of norms of weights, because it's going to show up a lot actually in both in this talk as well as the next talk. So rather than just the sum of the squares of the weights, there's been recent work that's been advocating that products of weights is a good regularization, and they have been deriving bounds on generalization for that. But there has also been this work coming more from information theory. In the previous talk, there was this encoder-decoder architecture, kind of arguing about information bottleneck, that I need to make things smaller in the middle. So there is actually a theory of information bottleneck connected to information theory, and there are people that are trying to use that to actually measure the capacity of the network, so that you actually put that as the regularization cost when you train them. So these are very nice, interesting papers that are just appearing. And last but not least is this question of optimization. I mentioned it earlier, we would like it to be convex, but it's not. Lots of global minima or local or saddle or flat regions. So the key question is, how does it really look like? How can I design methods to guarantee optimality? And the other thing, and this is kind of the most interesting and maybe the biggest mystery, is we are solving this gigantic optimization problem over 60 million variables, likely very messy, likely very complex. And we are choosing the simplest possible optimization method, namely gradient descent. Yet, it seems to be working. So I think the biggest mystery is trying to understand why stochastic gradient descent is so successful at training and finding good global minima. What I would argue, and this is maybe what people are trying to prove these days, is that the reality is that because the number of training examples is so tiny, teeny relative to the size of the network, then there are many global minimum. And what's going on is that stochastic gradient descent, because of the stochasticity, it gets out of sharp valleys like this, and maybe it ends up in wider valleys like that. And wider valleys, the conjecture is that they generalize better. Okay? So proving that and making a rigorous theory out of it is one of the key questions. So, again, this is not new. In the 80s, people studied the optimization heavily. And there was a very good result back in 89, where they say that if the network is linear, namely there is no nonlinearity, and it's just a single hidden layer, then you can guarantee that there is no, this word spurious is very used these days, spurious local minima. So what that means is that there is no local minima that is not global. So going back to the picture, this guy over here is guaranteed not to exist, okay? But other than that good result, almost anything else was really bad results. Actually, probably this was one of the reasons that people abandoned, from a theoretical perspective, the study of deep networks. What were the bad results? One, backpropagation fails to converge as soon as you add the nonlinearity. Second bad result, it would only converge if the data is linearly separable. Okay, so class 1 is here, class 1 is there, I can have a boundary. Do you really think that computer vision is like that today? Probably not. So kind of very strong assumptions. The other one, as soon as you have multiple layers, is full of local minima and plateaus. Okay? So I think, again, those were the reasons I say, okay, let's just do SVMs. This is way too complicated. It's never going to work. Again, lots of research in the last 10 years on trying to understand the optimization. Let me just emphasize that there is work trying to figure out why stochastic gradient descent is working. There are lots of connections between statistical physics and optimization these days. But let me now point out to the one that I'm really going to talk about, which is this one at the bottom, that really, again, is about products of weights, that if you regularize networks with products of weights, you can have guarantees of global optimality. So what makes doing theory of deep learning very hard? I think it is that these questions are not independent. Like in the past, architecture, design, or approximation theory, well, you give that to the people in harmonic analysis. You know, they do approximation all the time. Optimization, well, you just give that to the optimization people. And then generalization, well, you give that to the machine learning people. But the problem is that you cannot do these things separately anymore. Let me give you one concrete example. If you do this for SVMs, because the problem is convex, the optimizer is guaranteed to find the global minima. So then now you can just say, here's the global minima, analyze it independently. But now the situation is not like that. So obviously, there is this guess, which is probably true, that optimization can impact generalization. Why? Because maybe stochastic gradient descent is choosing one global minimum out of the many that happens to generalize well, right? And why does it so? We don't know. The second one is obviously the architecture has a strong effect on generalization. That's a little bit clear, right? Bigger architectures will approximate more functions. Smaller architectures will generalize better. But this is the third point, which is that maybe some architectures could be easier to optimize than others. There is actually an increasing number of papers whose results are of the form, if the size of the network is big enough, then there is no bad local minima kind of results. So size and how the architecture is organized seems to be playing a role in optimization as well. So what I'll be presenting today in this first lecture, and a little bit of the second, is this emerging theme of products of weights that I've mentioned before. It's just the tip of the iceberg. It's a tiny, teeny thing, but it's maybe the first connection between the three topics at trying to unify them. So there has been this work trying to, and this is going to be my second lecture, by the way, showing that dropout is an explicit form of regularization, and it shows up with a product of weights in there. The second one is that if you do regularize with a product of weights, then you have good theorems about the generalization performance of the network. And the last one, and this is what I'm going to talk first, is that if you regularize with a product of weights, then there is guarantees of no spurious local minimum. All right? So, again, the first part will be the analysis of optimization. What properties of the architecture make optimization easier? What properties of the regularization function make optimization easier? And here's going to be the two theorems I'm going to go through. Theorem number one. If you have a network like this with a lot of parallel structure, and you happen to find a local minimum such that all of the weights of one of the parallel subnetworks are 0. So all local minima such that all of the weights from one subnetwork are 0. That is a guarantee for it to be a global minimum. Okay? So that's going to be, I'm going to spend the rest of this talk trying to explain this theorem. The second theorem that I'll try to explain is the following, that if the size of the network is sufficiently large, some local descent strategy, not necessarily gradient descent, but maybe gradient descent augmented with something, can reach the global minimizer from any initialization. Okay? And again, this will be true not for any network, but for some very particular classes that I'll be speaking about. So this will be the first lecture before lunch. After lunch, I'll speak about dropout. And I will try to ask the questions, what objective function is really being minimized by dropout, if any, or is it just a random procedure? What type of regularization is induced by dropout? Is it really implicit or is it explicit? And what are the properties of the optimal weights? Like, can you actually prove this guess that everybody has around, that the weights are more or less equal? What is the exact definition of that? So this is going to be the 3 theorems. I forgot to change the number, so that should be 5. So I'm going to show that for linear networks, so for simple cases, dropout is equivalent to stochastic gradient descent. Okay? For some particular objective that is not the same as the one that you think is minimizing. So actually, dropout minimizes an objective that is different than the one that you think is minimizing. The second theorem is going to be that it induces an explicit formal regularization, and is in fact a low rank style. And for those of you who know what nuclear norm is, it induces the nuclear norm squared. And I'll explain that as I'm talking about. And the last one is that it really induces a notion of balanced weights. So we can make very concrete what it means that the weights are approximately equal. So there is actually an equation describing it. Okay? All right. How much time do I have? 15 minutes? Or can I? Huh? So what do we do? I just cut at 15 and then move the rest of the talk to the second part? Okay, 20 minutes. All right, so this is the work of Ben Haefele about the global optimality. Give me 1 second. Okay, so these are going to be, most theorems are if these conditions are satisfied, then this result is true. So these are the conditions. The architecture needs to be positively homogeneous and have parallel substructure. Okay, what does that mean? So let me go through each one of the assumptions. Positive homogeneity. So here is, I'll begin with a network. It has 3 weight layers, W1, W2, W3, and the output is going to be Y, okay? Because my goal is optimization, and my goal is global optimality, I'm going to think of Y as a function of the weights, right? Because I'm going to think of the input as being fixed, right? You've got your training set X, you've got some training examples for Y. My goal is to optimize over W. So what is this positive homogeneity? So scale the weights by alpha and assume that the alpha is non-negative. So we are going to make the assumption that if you scale the weights, the output is also scaled by alpha raised to some power. Okay? So here is more written in equations. This phi is the input-output map. So given the weights, it produces the output. If you scale the weights, then it scales the output. And there is this degree business in there that I'll talk about in a moment. Okay, sounds like a weird thing. Why would I require the network to do this? In fact, it's not even a requirement. This actually happens already in practice for many of the networks you guys work with. So let's think about the simplest one. Just 3 weights, dot product with the input, produces the output. A linear thing, fully connected is what I should say. Well, if you scale the weights, well, you just scale the output, right? It's a linear thing. So that's the definition of linearity. So nothing much. But let's talk about the ReLU, which is in here. So I'm going to scale the input to the ReLU by a non-negative scalar. So I'm going to put the alpha there now. And now I ask you, if I scale the input, does it change which one of the two is the maximum, or does it not? The answer is that if the alpha is non-negative, it does not change which one is the maximum. So you can take that alpha outside, actually. Because the ReLU is kind of a linear thing. So, the answer actually is in the linear part is linear. And in the negative part, well, that's why the alpha is not negative. So that's why we require homogeneity, but it needs to be positive. And the positive is precisely with the ReLU here. So the conclusion is that if you just have a linear layer, and this is true also for convolutions, which are also linear. So anything linear and ReLUs is positively homogeneous of degree 1. You scale the weights by alpha, the output is scaled by alpha. Okay, good. Let's do something a little bit more complicated. So now I'm going to have my input. I'm going to scale the weights of the first layer by alpha. It's convolution plus ReLU, so I already convinced you that the alpha goes out. Let me now do the second. I'm going to scale that by alpha. Because the input was already scaled by alpha, what's going to come out here is now alpha squared. Right? Instead of just alpha. Because it's the alpha from there and the alpha from there, I get alpha squared. Now I'm going to do another nonlinearity called max pooling. What is max pooling? Is just you just take a region of the image and you take the maximum response. So mathematically, this is just, I'm doing it with 2 variables, so this is 2 pixels, so it's a bit silly. So you scale each pixel by alpha squared, and you scale by alpha squared. What about the maximum? Well, the maximum is scaled by alpha squared. Which one takes the maximum doesn't change, because the alpha is non-negative. So good, the alpha square went to the other side. And the last one, again, I multiply by alpha there. I've got an alpha square there, so alpha cube comes out, and so I get alpha cube. So in conclusion, every layer that I add multiplies by alpha. So I get alpha, alpha square, alpha cube. So more generally, if you have a network with k weight layers, the output is homogeneous of degree k. So the homogeneity is just the number of weight layers. Is this always true? Well, it's true for convolutions, ReLU, max pooling, linear layers, mean pooling, but it's not true for sigmoids. It's not true for sigmoids. So that's the first conjecture that, I said that people argue, oh no, this vanishing gradient problem is the reason. So at least here, I'm going to have a sufficient condition that says that if your network has ReLUs or many of these other possibilities, we can have some guarantees of global optimality. But if you have sigmoids, we cannot. Okay, so that was the first point. We will require the architecture to be positively homogeneous. Second problem, we want the architecture to have parallel subnetwork structure. What does that mean? So think about this. I'm going to call this a subnetwork, but it's just 1 neuron here, 3 inputs, 2 outputs. Okay? And now repeat it many times in parallel and add them up to produce the output. So what is this? It's just a network with a single hidden layer. And such a network has parallel architecture. And the subnetwork is just a single neuron. So that's a trivial example to which our theorems will apply. Okay? The other thing I'd like to mention is the notion of size. Here is very easy to measure. It's just the number of neurons. Okay? Because there is just 1 layer. That's the only quantity. In this case, is the number of neurons. Okay, what about something else? Let me now pick this thing as the subnetwork, whatever you want, as long as it's positively homogeneous. Put 1, 2, 3, however many you want in parallel with each other. I'm requiring the architecture to be the same. So number of layers, number of neurons in each layer. But the weights across different subnetworks could be different. Okay? So this is, again, something that will be tolerated by our theorems. So in a sense, you start to get the sense that there is maybe the theorems are not good enough because we are going to be mostly concentrated on wide networks. But the good news is that it allows us to measure size easily because the size is going to be how many parallel subnetworks you have. So just 1 number, as opposed to the more complex situation you really want, which is how many layers and how many neurons. So you could now get fancy, right, and just declare your subnetwork to be the AlexNet and put many AlexNets in parallel and add them up. And that would also be a network with parallel substructure. Okay, so good. So again, I repeat, the conditions are if the architecture is homogeneous, okay, that's almost always the case. If the architecture has parallel subnetwork structure, okay, networks with a single hidden layers are good examples, but maybe most networks today, people don't put 100 AlexNets in parallel. Maybe you do in dropout because you're just training them multiple times and then you average them, right? So maybe there is something to this that we don't know yet. So I actually conjecture that there is some connection between dropout and this parallel architecture, and that we don't think we're using it, but we might be. Okay, so that was the first conditions of the theorem. The second one are regularization properties. And this is the mystery. The same thing that showed up here shows up there. Positive homogeneity. What do I mean by that? This is the way in which networks were regularized in the 80s. This is the way in which support vector machines are regularized. How? Sum of the squares of the weights. That's what you have in there. What is the degree of that thing? Is that homogeneous, and what is the degree? Can anyone raise your hand and tell me what is the degree of that as a function of the weights? You're all hungry, I understand that. But if you don't answer the question, then we'll wait longer. Okay, yes? 3? Good question. I'm asking about the degree of this map as a function of W. If you scale W by alpha, what do you get? Huh? Squared, so it's 2. Okay, and she said 3, but let's actually look at that in more detail. Indeed, the regularizer is of degree 2, but the network is of degree 3 because it has 3 weight layers, right? And here's the most important part of this talk. 2 is different from 3. And you're laughing, but the fact of the matter is that that is the source of the bad local minima. That if you had regularized with the same degree, that's when we have theorems that guarantee that they don't exist. But you can actually show that this generates some imbalance. So for networks with a single hidden layer, then the degree is 2, and then weight decay is good. But as soon as you have 3 layers, you should have used a degree 3. And if you have 100 layers, you should have used a degree 100. And we don't do that. We just tried degree 2 and it didn't work out, and so then we did drop out. Or early stopping or something else. Okay. So, how do we come up now with a regularizer that is degree 100? Sure, I could just raise things to the 100. That would be one way to do it. But here's another way to do it that makes sense, because you want the regularizer to measure the complexity. You want to measure the capacity of the network. So here's how we do it. So this is my network, lots of parallel structure. I'm going to first just pick one piece. That is my subnetwork. It has 5 layers in this particular case. So 1, 2, 3, 4, 5. Those are the, and the sub 1 is because it's the first subnetwork. So what I'm going to do is that I'm just going to define a regularizer for this subnetwork, and it needs to have 2 properties. First, it needs to be positive semi-definite. I don't want to explain that, but the intuition is it just needs to be non-negative. Think about a quadratic, if you want to think about something concrete, at least. Something that is bounded below by 0 and kind of grows with the weights. But the second one is exactly what I just said. We need the regularizer to have the same degree as the network. So that P and that P need to be the same in there. Okay? That's the requirement. Okay, so that's going to be for one subnetwork. Then, here's an example. You take the norm of the weights from the first layer. You multiply them by those of the second. Multiply, multiply, multiply. That's exactly that product of weight stuff that I was telling you about earlier. That product of weights is a good regularizer. Here we go. So if you take the product, by construction always, it will be of the same degree. 5 in this case. And then, that's for one subnetwork. In order to measure the complexity, we want this regularizer to get bigger and bigger and bigger as I add more stuff to the network. So that's what we do. The total regularizer is going to be the sum from 1 to the number of parallel subnetworks of the regularizer for the ith network. So this R is going to be my parameter for size. And that's what I'm going to try to regularize. So the gist of it is the following. Rather than sticking to a fixed network, we're going to allow the R to vary. We're going to say, what if R is equal to 1? What if R is equal to 2? Let's increase. Let's add more neurons to the pot when we optimize. The idea is that as I add more neurons, I will penalize by another term. And therefore, this regularizer will truly control the capacity of the network. Will control the size in terms of number of parallel subnetworks. Okay? So that's the summary. This is the theorem. Is going to be if the architecture is positively homogeneous and parallel, if the regularizer is positively homogeneous of the same degree as that guy and adapted to the network structure, then and I'm going to go back to the beginning of the talk, then we've got these two theorems that I mentioned. Where are they? Here we go. Then, theorem 1. All local minimum such that one parallel subnetwork, all of the weights are 0, is global. Theorem 2. If the size R is bigger than something, the local descent can find the global minimum from any initialization. So what it really means is that this is the typical landscape of a non-convex function, but these local minima are guaranteed not to exist when the size of the network is large enough. Okay? I will do the math and the equations as to why this is true after lunch, and I will therefore finish 2 minutes earlier. Inspired silently.